Hello and welcome to this video. In this video we are going to go through the capacitors practical for A2 physics. Now the capacitors practical is one of the few practicals that you do in A-level physics where you actually have an end goal, you have a value you're trying to get at, not just a proportionality or some kind of relationship that you're trying to prove. Now the case for this is, the way I'm going to set it up is we're going to try and determine the value of the time constant. Okay, so we're going to try and determine RC. Now, there are obviously variations of this. Your teacher or supervisor might tell you, okay, I'm going to give you this capacitance, or I'm going to give you this resistor, and I want you to use this method to then calculate what the capacitor is, or what the capacitance of the capacitor is, or what the resistance of the resistor is, or either. Okay, now the way you would do this will always be the same, so your method will remain the same. It will just be your analysis that changes, so everyone can follow this, but your analysis, I will explain where these things will differ at the end. Now, the way to determine RC, we need to think about what equations are we familiar with that include the time constant, and the only equations that should come to mind are when we're charging or discharging a capacitor. Now, for charging and discharging a capacitor, we have to first set up a circuit that we can choose whether we want to charge or discharge, and which one we actually want to measure. Now, our circuit is going to be similar to what we've said before, so we have a circuit with some sort of battery. Remembering, this has to be an AC supply. I am just doing it as a DC supply in this. If I were to draw it as an AC supply, it would look something more like this. Now, that AC supply needs to be parallel to a capacitor with some capacitance C. I'm also going to put an ammeter in here just to make sure that I have some amount of current. And at the edge here, I'm going to put a two-way switch, so it could either be in this, which is position 1, or it could connect here, which is position 2. Now in position 2, I'm then going to have a fixed resistor of resistance R, and I'm also going to put a voltmeter across R. And this is going to be the circuit setup. Notice I've used R and C, but I don't exactly know what those values are. Now, one thing that I should make clear in this is that if I'm going to use an ammeter and a voltmeter, you'll find that in the method that I'm going to use, I won't need an ammeter, but I will need a voltmeter. And I can't use a digital voltmeter or a digital ammeter in this experiment because I've got an alternating current. If I used a digital voltmeter, so a digital voltmeter, it will read a certain value and it has a certain refresh rate. So maybe it will read like one value every half a second or so. But that's too quick for me to read, right? I'm just going to see like blinking numbers and it's not really going to mean anything. So because this reads only one value at a time, right, and it has some kind of refresh rate, I don't want to read a digital voltmeter. Okay, I want to read an analog voltmeter. Now, an analog voltmeter will allow me to observe the change that's happening more visually, rather than trying to plot down all these numbers. And the way an analog voltmeter works is it will show a continuous change. And the display of the analog voltmeter looks something like this. So you'll have this curved section here with all these readings, which are just basically your voltmeter readings. Then you'll find that you'll have a section underneath this that is very useful. And then you'll have the dial here that will then basically just be able to move backwards and forwards depending on what direction everything's going in. Now, the section here, which is really important, is actually a mirror. And this mirror is entirely based just in order to make sure that your readings are accurate, and so you reduce parallax error. If you remember what parallax error is, it means if I were to tilt my head to the side, I would end up reading a different value than the one that I should be reading. The way this mirror works is that if the dial looks like this and I can see the reflection in the mirror like this, it means that I'm not looking completely parallel to this display. So it means that I'm going to read the incorrect value. So what I need to aim for is I need that reflection to be exactly underneath the dial itself. Okay, so I should see no reflection. And that's how I know that I have an accurate reading. Okay, and what I'm going to do first is I need to choose out of the two of charging and discharging, which equation is it going to be easier to work with to try and manipulate to get just the time constant. And what you find is it's much easier to manipulate the decay of charge or the discharging equation than it is to manipulate the charging equation. Now, the discharging equation is that V is equal to V naught e to the minus t over RC. Now, this tells me that I need well, my two variables here are going to be the voltmeter reading V and the time reading, which means I'm also going to have some sort of stopwatch here in order to account for the time. And then I can see that V0 is going to be a constant because that's just going to be the maximum potential that I can charge this capacitor up to, and RC is obviously a constant because that's the time constant. So that means that what I have to do is I need to first charge. So firstly, with the switch in position 1, I need to charge the capacitor. Now, the reason that I am choosing here to use the potential rather than the current is purely arbitrary, right? It's just I find it easier to use potential to read potential than to read current. But if you wanted to, you could just as easily go for the current and then calculate the rate, the time constant from that. The only issue with the current is that you will have the same trend when you're charging and discharging, so you won't be able to repeat this experiment the other way around. Okay, with the way I'm going to explain it, I'm only going to explain the discharging, but you could do a very similar method for the charging of it. Take potentials across the capacitor and then see what the capacitor reading would be, or what the current reading would be for each of those times. But I think for the most part, most teachers or supervisors will always make you do this reading of the analog voltmeter to try and read how the potential decays. So firstly, I'm going to charge the capacitor. Now, the reason I've got an ammeter in here, even though I'm not going to measure the current, is just so I can basically read off when I've fully charged the capacitor, because I want to have this capacitor reading as charged as possible. And when I do that, you could easily put in maybe a second voltmeter here just to read the potential across the capacitor when it's fully charged. When it's fully charged, I'm going to read a current of 0. So the current should be 0 amps or very close to 0 amps. And then I'm going to switch it to position 2. Switch to position 2. And for regular time intervals, I want to read the potential across this resistor. And for regular time intervals, read the potential on this analog voltmeter. Now, I need to make a table out of this, but I first need to think, if I want to calculate this rate constant, with all of these experiments, I always want to set up a straight line graph. So I need to manipulate this equation to get it into a straight line form. Now, we looked at this in the videos on capacitors, but I'm going to just re-go over it very quickly to see how I could change this equation into y equals mx plus c. Now, the first thing I need to do is make it just so I have the exponential term is equal to v over v naught. Then I'm going to log both sides, so I get minus t over rc is equal to log of v minus log of v naught. And I know I want my y-axis to be based on the potential, and I want my x-axis to be based on the time. So I'm just going to plus this log v naught over to this side, and I will then end up with an equation which is log of v is equal to minus 1 over rc times the time plus log of v naught. Okay, and this is now in the form of y is equal to mx plus c. And now I can then make this table, because my table has to include the actual readings that I want to plot on the graph. Now, what I want to plot is a graph of log of v against t. Okay, so what I'm going to do is I'm going to have a table where I have the time in seconds. I then want to have the voltmeter reading in volts. Then I'm going to convert that voltmeter reading into log of v. And then I'm going to plot a graph of log of v against t. So I have here log of v against t. Now, from this equation, what we're expecting to get is something that looks like this. So we should get a straight line graph with a negative gradient. Okay, and the gradient here is going to be minus 1 over rc. So therefore, we can say that the time constant rc is going to be minus 1 over gradient. And this is then determining this rate constant. We could also label on this graph that this y-intercept here is going to be log of v naught. Now, something to note here is, as we said at the start, if your goal wasn't to just determine what the rate constant is, you can then say from this, if you now know what the resistance is, you can basically just divide by the resistance to get the capacitance. And similarly, if you know what the capacitance is and you want the resistance, just divide by the capacitance and you'll get the resistance. Okay. Now, what I would specify is for any of these outcomes that you're trying to get, always check with your supervisor or your teacher or whoever's leading the practical to ask them what the actual value of that resistor or the capacitor is, so that you can calculate what your expected value is. Now, the reason that's going to be useful is because when you're writing your practical up and you're like completing your report and stuff, it's always good to refer back to what your expected value is versus the value that you actually got, because that difference is then going to tell you if your experiment was somewhat successful or somewhat not successful. And then from there, you can then build upon your conclusion, saying what do you think went wrong if stuff went wrong, or you can build upon your conclusion saying, yeah, everything was great. Okay. So hopefully this all makes sense. This is a pretty straightforward practical. It's just the analysis part that's a little bit tricky. But as soon as you plot out the graph, or you can rearrange the equation, everything else is pretty straightforward. Thank you for watching.